The first speaker now is Ted Jacobson, and his topic is Hawking radiation, infinite redshifts, and black hole analogues.
Is the mic on? So it's a real pleasure and honor to be participating in the celebration of Stephen's birthday. Stephen has done a huge amount to make this an incredibly fascinating field and incredibly successful field, and hearing about what's happened in it in this conference is exhilarating, really, and I feel like it's clear we're in the second century of general relativity, and all systems are go. So my talk will be about this analog Hawking radiation, basically, but I want to start by, so I'm assuming that there are people in the room who really barely know what Hawking radiation is and what it comes from, or why anybody would want to consider an analogy of it in condensed matter. So I just want to go back to a peculiar aspect of the history of the discovery of Hawking radiation. Back in the early 70s, Jacob Bekenstein was a graduate student. His advisor asked him, well, was discussing with him the issue that was mentioned earlier in the meeting, that it's apparently one could violate the second law of thermodynamics for the exterior of a black hole by just dumping entropy into the black hole, in this case in a cup of tea, so the entropy outside would go down. Bekenstein thought about it and I guess considered the fact that actually if you drop the entropy into the black hole, something changes, the black hole gets bigger. And so he got the idea to attribute an entropy to the black hole that grows when it gets bigger. Now, he might have thought it should be determined by the mass of the black hole, but that wouldn't be additive if you had, say, two black holes, but the surface areas would be additive. And also, he had the area theorem from Hawking, which was blatantly analogous to entropy. So he hypothesized that the black hole has an entropy proportional to its horizon area. And the coefficient, he reasoned, should be 1 over Planck length squared times some numerical constant. Planck length, in case you didn't know it, is an incredibly small length, 10 to the minus 33 centimeters. And he proposed a generalized second law, which is that although the entropy outside can go down, if you add to it this black hole entropy, then the sum could never go down. So the change must be non-negative. And he considered, there's a problem with this, which is it basically couldn't be true, because you could associate a temperature with the derivative of entropy with respect to energy of the black hole. The reciprocal of that, if it's really acting as a thermodynamic object, should be the temperature of it. But of course, the temperature of a black hole is 0 because nothing could come out of it. And that actually led to a contradiction with this generalized second law. If the black hole is immersed in a thermal bath whose temperature is less than this effective, this would-be temperature of the black hole, then overall the entropy would decrease, the generalized entropy. So an earlier talk discussed, I think it was Raphael Bousso's alternate histories. So one alternate history it's interesting to think about is that Bekenstein could have said at that point, okay, I believe in this generalized second law. I believe in thermodynamics above everything else. Therefore, a black hole must have a real temperature. And he would have asked himself, how could it possibly? Nothing can come out of it. But then he would remember that a black hole in space is not really isolated. It's immersed in the vacuum of quantum fields. And then he would eventually have discovered the Hawking effect. In any case, in order for the generalized second law to hold, this really must be a real temperature, and Stephen Hawking did discover that by considering a black hole immersed in the vacuum of quantum fields. But Stephen was not trying to check the generalized second law. He had a totally different agenda at that moment. He was trying to check the prediction of Zeldovich and others that a rotating black hole would spontaneously radiate by a pair creation process and radiate away its angular momentum. But then he discovered by accident this Hawking effect. So what is this Hawking effect? Here's a picture that I like from Roger Penrose's hand. a space-time diagram of the collapse of matter to form a black hole. And here's the matter. Here's the last light cone that's not trapped. And the future of this point in space-time becomes the horizon. This is a perfect symmetrical scenario. So the light cones are tipped inwards, and events inside this horizon cannot influence anything outside of it, because no influence can propagate faster than light. And things just barely outside can eventually climb away, but only after some peeling. And that peeling is described by a redshift factor that actually depends on how long the peeling has been happening for. So to quantify that, considering, let's say, a source that falls across the horizon here and is emitting radiation with a frequency omega naught, we can look at what would the frequency of that be when it's received up here, a time t later as measured by these asymptotic observers. And in fact, that frequency is redshifted by an amount e to the minus kappa t. Kappa is called the surface gravity of the black hole, and it's the speed of light for a spherical black hole divided by twice the Schwarzschild radius. So as time goes on, this exponential redshift factor gets arbitrarily small. I'll come back to that in a moment, but I just want to first explain where the instability that's associated with the Hawking radiation comes from. So once the black hole is formed, the space-time has a time translation symmetry, and here's a vector field showing how to shift the diagram in that symmetry direction. Inside the horizon, it's also symmetric, also by shifting the diagram upwards. But note that on the horizon, that upward shift is actually on the edge of the light cone, so it's at the speed of light. It's not a time translation, it's a light-like translation, and inside, it's a space-like translation. So the conserved quantity related to this symmetry is really like momentum inside here and like energy outside here. Energy is bounded below in a stable system, but momentum is not bounded below. And in fact, quantum fields inside the horizon can have states on shell that have negative values of this conserved quantity. And therefore, a process could happen that conserves this quantity, but involves emitting positive energy to infinity and correspondingly negative, quote, energy, namely conserved quantity, inside the black hole. And that's sort of the essence of the Hawking effect. But more locally or specifically, what is happening to the quantum fields? It's possible to trace it to a tidal effect. So the vacuum fluctuations at any 2 points in space are correlated, whether there's a black hole there or not. But if the horizon separates the 2 points, and we're considering a vacuum mode that's propagating outwards, then the mode or wave packet on the outside eventually peels away, like I was just saying. But the one on the inside, despite all its efforts to keep going outwards, is falling inwards to the black hole. And so this correlated pair of vacuum fluctuations is peeled apart, and it turns into an on-shell particle, and what's often called, it's the partner of that Hawking particle. And this happens to be something that leads to a thermal spectrum at the temperature TH, which is actually proportional to the surface gravity, h bar over 2 pi times the surface gravity. This, by the way, numerically, I put a black hole of the mass of the sun, but I think I should take 30 solar masses instead, in which case this would be 2 nanokelvin. So the Hawking temperature of the 30 solar mass black hole we just heard about earlier today is 2 nanokelvin. And I'll be telling you about other black holes, and you'll hear in the next talk much more about that, whose Hawking temperature is also of order nanokelvin, but they are a little bit smaller. Okay. Yeah, so I don't have time to explain where that temperature comes from precisely, so let me just not do that. Instead, focus on this infinite redshift aspect for a moment. So as I said, if we wait longer and longer, the outgoing frequency is related to the ingoing one here by an exponentially small factor. On the other hand, if we're looking at Hawking radiation, we want to fix the outgoing frequency to be of order the Hawking temperature divided by h bar, and trace backwards in time and see which vacuum fluctuations gave rise to that Hawking quantum. And so then we get the reciprocal of that redshift factor. We get the blue shift factor e to the kappa t. And after only 2 seconds for a solar mass black hole, that's e to the 100,000. So what this is saying is that when we derive the Hawking effect in the way I sort of just waved my hands a moment ago, we're talking about evolution of the quantum vacuum from frequencies that are absurdly high to low frequencies like corresponding to 2 nanokelvin. So the question is this an absurd extrapolation? More importantly, must we believe in it to believe in the Hawking effect at all? And a second question is this really how outgoing modes emerge from a black hole? Do they really come from essentially infinitely blue-shifted progenitors? So the answer to the first question is no. We don't have to believe in this absurd extrapolation because, as I've just circled here, instead of tracing, let's say, this Hawking quantum all the way back to the beginning of the formation of the horizon, we can just trace it back far enough until the sort of length scale associated with its wavelength and its frequency is very small compared to the size of the black hole. On the other hand, and that can be still very long compared to the Planck scale or any other scale that we feel is a frontier of our knowledge. And then at that scale, we can assume, we have to assume some condition, we can assume that whatever quantum gravity is, it adiabatically delivers the outgoing free fall vacuum inside this blue circle or ellipse at the scales that I just described. So it's a natural assumption because these tiny scales I'm talking about see this space-time of collapse as just a constant background. The time scale of the collapse is eons compared to a Planck time. So if the adiabatic theorem somehow applies in quantum gravity, it's natural to suppose that what we have here is the outgoing vacuum. And that's all we need to get the Hawking effect. And that's essentially why we feel confident in the Hawking effect, despite not knowing about the ultimate resolution of this infinite redshift puzzle. The second question, do outgoing modes really arise this way? I would say, who knows? In fact, I find this an extremely puzzling aspect still. Because of Lorentz symmetry, there's no preferred frame near the horizon locally. The black hole as a whole defines a preferred frame. So we could imagine logically that somehow the black hole spacetime non-locally produces the outgoing modes without ever passing through essentially infinitely blue-shifted progenitors. But that's a non-local process that we have no way of, I don't know how to even begin formulating that within local quantum field theory, for instance, or in quantum gravity. But I actually believe something like that must be true in quantum gravity, because the only alternative is that some kind of Lorentz violating process happens near the horizon, and as it does in the sonic models I'm about to tell you about, and instead resolves this infinite redshift puzzle in a different way. But I'm not proposing that space-time violates Lorentz symmetry. I think instead there's some non-local process that produces the true outgoing black hole modes. Okay, well, thinking about these kind of issues, back in 1980, Bill Unruh proposed the idea of sonic analog black holes in this paper, Experimental Black Hole Evaporation ? The full abstract is here. It's shown that the same arguments that lead to black hole evaporation also predict that a thermal spectrum of sound waves should be given out from the sonic horizon in transonic fluid flow. So here's a cartoon of that from a paper by Ralph Schutzhold. Here's fluid flowing from right to left. These circles represent the wave fronts of sound waves. And here's the place where the fluid flow velocity matches, towards the left, matches the speed of sound in the fluid. So sound to the left of this midpoint cannot propagate past the midpoint to the right. So this acts like a horizon in the fluid flow. And what Bill showed actually is the analogy is quite strict mathematically. You can write down a line element for a space-time determined by the velocity of the fluid and the speed of sound in the fluid, the density of the fluid, such that the sound waves propagating on the background of this fluid flow satisfy the covariant wave equation of a scalar field. Actually, it's the velocity potential for the sound waves satisfy the covariant wave equation in this metric. So then we could look at the horizon in this metric and the surface gravity in this metric, and it turns out to be, given the surface gravity is just the derivative, it's the rate of change of the velocity evaluated at the horizon. Actually, that's true. Bill was assuming a kind of like water, an incompressible fluid, so that the speed of sound was just constant in it. But if the speed of sound is not constant, then actually the correct formula, you replace v by v plus the speed of sound. And that's actually the regime, the situation in Bose-Einstein condensates, as you'll hear about. So given this sonic analogy, that opens the opportunity to study, both in theory and in the laboratory, in a setting where the underlying physics is completely understood. It's just quantum mechanics of atoms, I guess. The origin of the outgoing modes, given an atomic cutoff, whether or not the outgoing vacuum really is adiabatically delivered by whatever process is happening at the atomic scale in the fluid, and the wider validity of Hawking's prediction, not just for black holes, but for these analog systems. So when I started thinking about this, it was before Bose-Einstein condensates had actually been realized in the laboratory. So the only zero temperature fluid that came to mind was superfluid helium-4, or the simplest one that did. And I started reading up on it and learned that one of the first things you learn is here's the dispersion relation for perturbations of superfluid helium-4. This is momentum or wave vector and frequency. And at long wavelengths, it's linear. So that describes the sound regime where the speed of sound is independent of wavelength. But once the wavelength starts to approach angstrom scale, which is the separation scale of the atoms, the group velocity, well, the curve drops over, the group velocity drops, and eventually it does this funny wiggle associated with what's called the Roton minimum. And eventually, at high enough wave number, there just are no stable excitations or quasi-particles. So we could ask, with this situation, what would be the origin of the outgoing modes in Unruh's sonic analogy? And we can, basically, the conclusion is it would be something like this. An outgoing mode traced back to the horizon would be blue shifting. That means on this curve, it would be running up here until eventually it reaches the point where its group velocity has dropped to be equal and opposite to the flow velocity. At that point, it can't get any closer backwards in time than that point to the horizon. And instead, it actually turns around at a turning point and goes further out. And that's what happens over, actually it depends on the exact value of the frequency, but it goes over this hump and turns around. But because this has a couple of wiggles, in fact, you find that the precursor of the Hawking mode does this dancing outside the horizon. Eventually, it gets pushed off to this part of the dispersion curve, where it actually decays backwards in time into a pair of rotons. And you see that the origin of the outgoing modes in this superfluid helium-4 model is some kind of collection of microscopic excitations of the fluid that sort of come together teleologically, because I put a final boundary condition on, to produce this outgoing mode. So it's kind of complicated. And in fact, it seemed like, I mean, how would we begin to study Hawking radiation in a system like this? Or do we have to do the many-body quantum mechanics of this system. But actually, it turns out that we don't, because the dispersion relation already tells us a lot. And in fact, if we eliminate this complicated bump and wiggle, we can really do a lot analytically, even in linear field theory. And that was actually Unruh's observation also after I pointed out this kind of behavior of the wave packets. Actually, I didn't point out the full thing. I was confused at what happened at this turning point. It seemed that the wave got stuck and I didn't know what happened next. But Bill figured out what happened next. Okay, so we could consider then, like I just described, a subsonic type dispersion. Here's the relativistic one, or supersonic. This is the one I'll focus on mostly later because that's the one that applies for a Bose-Einstein condensate. Now, in general, what would happen to the Hawking pairs in these different scenarios? First, the relativistic case, the pairs trace backwards in time. They just squeeze closer and closer to the horizon.
Call this.
Could somebody tell me what he said?
Keep going.
Okay. Become arbitrarily blue shifted. In the subsonic or subluminal case I just described, the pair actually comes from outside. In the case where it decays, it's unstable, it sort of dissolves into the soup outside or around the horizon. And by the way, a model describing precisely that process using linear field theory was worked out recently, very recently, by Robertson and Parentani. And finally, in the superluminal case, well, then the mode, if it blue shifts enough, its group velocity gets high enough that it can scoot out across the horizon and escape from the black hole. Okay, so numerous studies with linear field theory and different dispersion relations have shown that the Hawking effect is robust to this sort of a modification of the short wavelength behavior, provided A, the incoming field is in its ground state, sort of in the flowing fluid. The perturbations start out in their ground state. And that the cutoff wave number, the scale at which the dispersion starts to be nonlinear, should be much higher than the surface gravity of the black hole. Or kind of roughly what this is saying is the wavelength at which that happens should be small compared to the size of the black hole. Actually, it turns out that the Hawking effect is even more robust than that. You can get away with having the cutoff not so much higher, or maybe not even at all higher than the surface gravity, provided that the flow has a very long stretch of constant rate of change of the velocity, that is constant surface gravity. And for the current state of the art on these issues about the robustness, see these recent papers by Parentani and his collaborators. So many candidates for actual experimental systems like this have been considered. I don't want to spend time reading the list, but I will focus on the Bose-Einstein example. So a Bose-Einstein condensate has a dispersion relation like this. So at small enough wave vector, all we have is the first term. Higher wave vectors, we have this term. This is just linear with a speed of sound, cs, determined by the density of the condensate, a coupling constant that's determined by the scattering length and the mass of the atoms. So this is a constant if the density is constant, but a Bose condensate is not an incompressible fluid. So in fact, in general, the speed of sound in it will be position dependent because the density is. And this term is actually, if you just look at it, if you multiply both sides by h bar squared, you just get the energy squared here, and you recognize this is just the non-relativistic kinetic energy of an atom. So the dispersion relation interpolates between sound and just atoms ballistically moving with a non-relativistic energy. So let's consider this dispersion relation and ask, how do the outgoing, in this case, more specifically, how did the Hawking pairs arise? I could, yeah, instead of tracing just an outgoing, pure outgoing mode backward, I'm going to start with something inside. You'll see why in a couple of slides, because in an experiment, that's actually, it turns out what's happening in one experiment. So let's suppose we have an outgoing superluminal or supersonic mode that's heading for the horizon. Now I have to actually specify, here's a dispersion relation, the square root of k squared plus k to the fourth term times the speed of sound. And because of the flow, there's a Doppler shift between the frequency wave number relation in the fluid frame and the corresponding relation to frequency in the static frame in which the flow is static. And that Doppler shift formula is just given by this. So the fluid, the static frame velocity, frequency is conserved because, to the extent that the flow is static. That's just the conserved frequency. So this defines a straight line with intercept given by that static conserved frequency and slope given by the velocity of the flow. So I've plotted on here 3 of those lines, one subsonic, one supersonic, and one exactly, it's still supersonic, but it's tangent to the curve right there. So now we can see what happens. Suppose we start out with this root of the dispersion relation. You can see that the slope of this curve, which is the group velocity, is greater than the slope of the straight line, which means that this corresponding wave mode is propagating to the right. Here it is. It's moving towards the horizon. The velocity of the flow is dropping as I reach the horizon, so the slope of this line is dropping with the same intercept. Eventually, it drops to this point of the purple line where it becomes tangent, and that's a turning point. And then what happens is it continues on this curve and goes back out the other way, once again to higher slope, but now it's got a small wave vector. So that's what this curve is describing. On the other hand, I'm using WKB approximation or language to describe what's going on to these waves. Really, they're waves. And the WKB approximation breaks down at this turning point. And so actually what happens in the wave is that a branch of the dispersion relation up here is excited. Actually, sorry, up here, let's say. And now that corresponds to a velocity that's greater than the flow. And it can simply propagate outward upstream of the horizon. As it does so, the flow velocity is dropping, let's say, if it's smaller flow velocity here. And that migrates down to this point on the dispersion relation. So this is an example of the way a pair mode is populated. It's not the only case, because I could have also started, instead of with this mode, I could have started with the one up here. And then what we would have found is that that mode continuously propagates across the horizon, but the breakdown of WKB leads to a partner mode on the inside as well. And we should consider both of those to formulate the correct positive norm modes that we use to quantize this perturbation field. That whole quantum aspect I'm not going into in detail here. So this should show how in this kind of a system those modes can be created. Okay. Now there's this positive negative energy point I mentioned earlier. I just want to point out that if we look at a light cone here of the acoustic metric inside the horizon, and the killing vector is this vertical vector, the inner product of an outgoing light ray, which would be on the right-hand side of this light cone, with the killing vector would be negative, where if I use a plus, minus, minus, minus signature, and whereas the inner product with an ingoing light ray would have a positive inner product. That just means that this ingoing one is a positive energy excitation, and this outgoing one has negative energy. And so the one I was actually describing on the previous slide is a negative energy excitation. Now, so far I've only talked about one horizon, but in the laboratory experiment, in fact, it turns out it's natural to create a flow that has a second inner horizon, or a white hole horizon, where the flow velocity once again drops below the speed of sound. And that creates an ergo region between the two where the flow is supersonic, and inside of which negative energy modes are trapped, like they're trapped in the ergosphere of a rotating black hole. And that means actually that there's a superradiant instability that can happen here, which Steve Corley and I called the black hole laser. And basically, it's very similar, if you were familiar with the superradiant instability that was mentioned earlier about light mass scalar fields around rotating black holes. It's essentially the same kind of a thing, although in that case, the instability is the buildup of negative energy modes in the ergo region is limited by the fact that they also fall across the horizon. Whereas in this case, the ergo region is just bounded by these two horizons and the modes are trapped. So one sees actually that there would be an instability here. I don't have time to explain it in detail. And this seemed very interesting and eventually got considered to be a possibly good target for experimental verification of Hawking effect in the lab, because rather than detecting the very delicate signal of a single Hawking pair, maybe one could detect this exponentially unstable scenario. So Jeff Steinhauer, who'll speak next, has done a lot of work on these Bose condensates and developed the ability to create flows that have horizons and to measure what's happening inside those flows to the flow and the phonons. And one of those experiments is one that my collaborators and I have modeled. Actually, several groups have been modeling this experiment, including Jeff's group. The basic setup of the experiment is to take a condensate in a trap that's very narrow, like this stick or something, and then sweep through the condensate a step in the potential that drops down. So imagine that step goes down like this, and I sweep it from this side to that side. Well, then the atoms that are on this side can fall down farther in the potential, and so basically like a waterfall is created as atoms flow from this static part of the condensate over the edge of the step and over here. But then the trap potential goes back up on this side, so the flow velocity slows down again. And that creates the white hole horizon on this side. The step is moved at a fixed velocity, and in the reference frame of the step, the fluid is flowing the opposite way, and that creates one of these white hole, black hole pair scenarios. Here's a plot, for example, of the velocity of the flow, actually minus the velocity of the flow. It goes up in the middle, comes back down on the other side, and the speed of sound, as I mentioned earlier, is not constant because the flow, of course, in the supersonic region, the flow has lower density to conserve the number of atoms. So the flow velocity drops, and the horizon is where the speed of sound is equal and opposite to the flow velocity. And then there's a white hole horizon. So how much time is it? Down to? It's down to about 2 minutes. OK. So here's a picture that Jeff made of the condensate, a time series of images. One can see very sharp transition here between the subsonic and supersonic region. And what appeared after time is a kind of oscillating density pattern between the two horizons. And one can simulate the experiment using what's called the Gross-Pedievsky equation. It's a nonlinear Schrodinger equation that describes the condensate wave function. And the way we did this in our group to try to understand what was happening is various different diagnostics on this wave function. Spectral analysis, but also these space-time portraits, which turned out to be extremely helpful to us. And I want to emphasize that right now I'm going to end by just telling you what we think is happening in this experiment. And it's not the same. Like I mentioned, several groups have studied this experiment and published papers about what's happening, and none of them came to the same conclusion that we did. So it should be considered, I guess, not established yet. But here's what we found. So what we're plotting here is the magnitude of the Gross-Pedievsky wave function. It's a complex function, so it's its modulus. Although on this side, we've subtracted out we subtracted out the very slowly varying parts so we could see the Hawking radiation on this side. Here, in fact, not only that, we've scaled by a factor of 10 in the density plot because it's very weak over here. So this corresponds to the parameters as best we could match them to the experiment. And then we also considered a slightly enhanced case, which was almost the same, but this trap was twice as large, and the potential step was half as deep. And that difference actually made a huge difference in how sharp the signal we could get was. But it seems like the same basic phenomenon is happening. And that phenomenon is the following, as we understand it. At the white hole horizon, a standing wave pattern is formed, and it's basically a bow wave. Just like if a boat is moving through the water faster than the speed of water waves, there's a standing wave pattern in front of the boat. That's this standing wave pattern. You can see that the wave fronts are running parallel to this boundary of the low density region, and that's the white hole horizon location. So this is a standing wave at rest in the frame of the white hole. But the white hole and the black hole are not at rest with respect to each other because the trap is shaped like this, and the step is sweeping, and just the place where the white hole occurs is just determined by some flow parameters and trap parameters over here, whereas the black hole speed is completely determined by the motion of the step. So in fact, the white hole lags behind the black hole, and that means because there's a Doppler shift, so this standing wave has a non-zero frequency in the black hole frame, and therefore it is able to stimulate the emission of Hawking radiation at that particular frequency in a classical process, essentially. This is not spontaneous Hawking radiation. It's just, it's like a coherent state of phonons inside the condensate stimulating Hawking radiation. You can sort of see the radiation here and the partners there. You can see it super clearly in this case. And I should just end by saying that we did a spectral analysis of this, confirmed that this standing wave, all components of this system of the waves have zero frequency when referred to the white hole frame. And we checked the Hawking prediction for the ratio of the amplitudes of the outgoing waves to the ingoing partner waves. And that, according to the thermal prediction, should have been exponential of minus pi over kappa times the frequency. Delta means relative to the background frequency. And then we sort of measured in the simulation what's this ratio of those two modes, and it agreed with the thermal prediction to within 25%. I should emphasize this is a very steep change in the velocity flow. Remember, I pointed to the transition. So it's as if the Hawking temperature is very high because the velocity is changing very rapidly here, and the density on the order of like the healing length of the condensate, a couple of microns. Nevertheless, we're getting a fairly good match to the Hawking prediction. And then I'll just end by a couple of comments. So the Hawking effect extends to acoustic analogues, and analogues regulate the infinite redshift and can be studied in the laboratory. The origin of the outgoing modes in space-time, as opposed to in analogues, remains, to me, totally puzzling. And in the next talk, you'll hear from Jeff about a different experiment designed to measure actual entanglement of spontaneous quantum emission of Hawking radiation phonons. And the era of experimental Hawking radiation has dawned.
Slava.
Could you comment, okay, because Bill Unruh also was doing something. Yeah, Bill Unruh also was doing something, okay, maybe not so precise experiment, but with liquid, right?
Yes, surface waves on water.
Yes, absolutely. So then, okay, it was realized that to some extent that it refers rather to white hole horizon, what he was doing with this.
Yes, they were, Silke Weinfurtner, I think, led the experiment, and they were launching waves towards a white hole horizon.
Yes, absolutely.
Of surface wave flow.
But here is, which horizon here is important more? Black hole or white hole in this experiment?
Well, if our interpretation of this is right, the presence of the white hole horizon generates that standing wave, the bow wave, which propagates to the black hole horizon and then stimulates Hawking radiation at the black hole horizon.
But this standing wave is not the same thing as I would say, quantum minimal fluctuations. Is a different story.
Right.
This is why, then you are measuring the ratio of beta to alpha squared, right?
Right.
So
And in fact, I should have said explicitly, I didn't, but so the motivation of having these two horizons was that maybe we would see this instability, the black hole laser superradiant instability. In fact, it seems like, at least with the parameters we're using in the simulation, there is no superradiant instability, at least not on the time frame we looked at. In fact, we think that what was seen in the experiment was what I just described, stimulated Hawking radiation by the bow wave mode. Maybe if you ran it for longer, you could eventually excite that other instability, or maybe slightly different parameters of the black hole.
Okay.
So you motivated at the beginning. You motivated things by tracing back the outgoing Hawking radiation to all the way right to the horizon. But I thought I should think of the origin of the radiation as kind of coming from something that's quite long, a long wavelength thing that's kind of sloshing around the zone between 2R and 3R.
Yeah, I don't think you can. So it's true that that's true in the sense if you look at something like the energy momentum tensor as the imprint of the presence of the Hawking radiation. But I think if you want to derive the fact that it's thermal radiation at a temperature determined by the surface gravity, you need to trace the mode back to the vacuum near the horizon. Like I said, it doesn't have to be ultra near, but it has to be near compared to the scale of the black hole. So it's a question of the sort of the origin, the ancestry of the radiation.
I think we should move on because we have to be finished by about 5:30 for the photograph. So thank the speaker again.